Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, welcome back to Physics with Beth and Beth. I'm Beth, and today we are continuing our discussion of AP Physics 1, Unit 4, which is on momentum, impulse, and collisions, and we're going to kick it off with a pretty fun topic today. So as you can tell from my festive attire, we are nearing Christmas time at the time that we record this video, but for the sake of this lesson, we're going to completely ignore that and skip straight past to New Year's. And how do we celebrate New Year's except by setting off some safe, family-friendly explosions? So today we're going to be talking about explosions and specifically how they relate to momentum. So let's say I've got a little firecracker here that I am setting off as part of my New Year's Eve festivities. And this firecracker explodes after I set it off. It lights and it breaks off into two pieces which go flying in opposite directions. And specifically, I'm going to say that it breaks off into two pieces. This is piece number 1 on the left, and this is piece number 2 on the right. I'm going to say that piece number 1, I don't know its mass, so I'm going to say it has a mass of m, maybe. But the piece on the right is much bigger, so I'm going to say that this has a mass of 15 m. It's 15 times as heavy as the other piece over here, as piece number 1. And the question that I'm going to have us all answer today, because I am a nerd and have not been and never will be cool, is how the change in the magnitude of momentum of our piece number 1 here compares to the change in the magnitude of momentum of piece number 2. Now, anytime you're faced with a question like this, the one thing I want you to remember before you think of anything else, the very first principle I want you guys to think about is the fact that momentum is conserved. That is one of the fundamental laws of the universe that everything and everyone has to obey, whether you're a person walking across the street or a galaxy moving through the cosmos. Momentum is always conserved. Okay, so what that means in the context of this problem is that our initial momentum of our system is equal to the final momentum because momentum is conserved. So conservation of momentum tells us that the momentum I start out with must be equal to the momentum that I end up with. My original momentum is equal to my final. Now, I'm going to be talking about the two different pieces of this firecracker. So my original momentum is equal to the momentum of piece 1 plus the momentum of piece 2. Okay, that's not so bad. The initial momentum of piece 1 plus the initial momentum of piece 2. Now, however, I'm not moving when I start out, am I? I just have a little firecracker that's sitting on the ground. I've just lit it and I'm booking it away because you always don't light firecrackers that are close to you. That's a little safety tip. Okay, but if my firecracker is at rest, it's not moving, well, that means that its velocity is 0, right? Momentum is equal to mass times velocity, should be a lowercase p, is equal to mass times velocity. So if my velocity is 0, then my momentum is likewise equal to 0. If I have no movement, I don't have momentum, right? So if both of my objects here, or my one object, my firecracker with two pieces, are both at rest, then my initial momentum is equal to 0. So my initial momentum is equal to 0 plus 0, which is equal to 0. All right, so that's the second idea I want you guys to really wrap your heads around in this video. If I don't have movement, I don't have momentum. If something is at rest, then its initial momentum is going to be 0 when I start out with. And if something ends up at rest, then the final momentum of that thing is going to be 0. So now you might be thinking, wait, but Beth, you were just talking about how momentum is always conserved if my initial momentum is 0, but I have movement, I end up having a final momentum, like this piece over here is flying off to the left, this piece is flying off to the right, or vice versa, however lefts and rights work, I don't know, then I have movement at the end. I should have a non-zero final momentum. So how on earth does that work? Well, let's talk about it. That's a great question, me. So we're going to have our final momentum, which is equal to the sum of the momentum of this piece that's flying off this way, plus the momentum of this piece that's flying off this way. So it's going to be equal to the final momentum of piece 1 plus the final momentum of piece 2. All right, now momentum is equal to mass times velocity. The mass of my first piece is just mass m. and I'm going to say that it has a velocity of v, of v1. The final velocity of piece 1 is equal to the mass of piece 2, which we know is 15m, times the final velocity of piece 2. So let me just move this down here, plus 15m. There we go. Don't forget the m. 15 times m of our final velocity of piece 2. All right. So now, if I want to solve for the final momentums of each piece relative to one another, I'm just going to move this momentum over here by subtracting it from both sides. Hey, this is my momentum of piece 1, right? And this is my momentum of piece 2, and they're equal to one another. So that's what we mean by the conservation of momentum. I start out with no momentum, and at the end, yeah, I have pieces that both have non-zero momentum, but because momentum is a vector, it has direction, they cancel each other out. Momentum here is pointed this way, momentum of this piece is pointed this way, and they end up having the same magnitude. So, in regards to that question that I posed when we started out with, how does the change in the magnitude of our first piece compare to the change in the magnitude of the momentum of our first piece compared to the change in the magnitude of our momentum of our second piece? They're exactly equal. The momentum of this piece at the end is equal to the momentum of this piece at the end. Now, but you might be thinking, wait, but this piece on this side is way heavier. Shouldn't it have more momentum? Well, you're right that it is heavier, but here if we solve for the respective velocities of each piece at the end, which I'm going to do by just dividing both sides by m. I have an m here and an m here, so if I divide by m, both cancel. I end up finding that my final velocity of piece 1 is equal to the negative of 15 times my final velocity of piece 2. So this piece is 15 times heavier, but this piece is moving 15 times faster, just in the opposite direction. So that's how we end up conserving momentum. Yeah, this piece is heavier, but it's also moving way slower. Yeah, this piece is lighter, but it's also moving way faster. They end up having the same momentum in opposite directions, so it cancels out all at the end, and we end up with a net momentum that's still equal to 0, just like what we started out with. All right, so our momentum was conserved. That's a big idea. Hold on to that. Don't forget that if you don't get anything else out of this video. Momentum is always conserved. Because we started out at rest, our initial momentum was 0, and at the end, the momentums of our respective pieces canceled out, and we were left with a net total momentum at the end that was also equal to 0. This piece was way heavier, but it moved way slower. This piece was way lighter, but it moved way faster. So everything ended up balancing out there. All right, thank you so much for sticking with me. I know that was a lot, but y'all are troopers, and I really appreciate all of you. A quick comment, if you guys are enjoying these videos, please just let us know with a like or a subscribe or a comment. I promise you, we read every single comment, and they always make our day. Also, another quick comment, if you like our little shirts here that Miss Beth and I are wearing from this point onwards, they're actually shirts we made, and if you want to, there's a link in our bio to our little Redbubble page and our TeePublic page where we have all of these nerdy little shirts that we made if you want to be cool and look like us, I guess. Anyway, that's all I have for today. Thank you so much for sticking with me through all of that. Y'all are troopers, and happy physicsing.